All right, hello recording. So this is the warm-up that we just finished. We are about to check our answers. So for the first 5 questions, you had to find the first partials. So there'd be a partial for every input variable. So you'll have 2 first partials for every one of these. The first one, you should have f sub x as 2xy e to the x squared y, and f sub y is x squared e to the x squared y. Check your answers. Put a little check mark if you got it, or a happy face, or some positive reinforcement symbol. Okay. I can't tell what he's drawing. Is that a duck?
Oh.
It's Mickey Mouse.
Oh, good. Okay, I like it. All right.
Flower.
I thought from here I thought it was a flower too. Okay. Letter B. So letter B is this polynomial. Answer 3. So the f sub x is 3x squared minus 4xy. F sub y is negative 2x squared plus 2y. Uh-oh. You guys dropped a negative. You got it? That looked like a little write-in there.
No.
Couldn't
tell with the equal sign. You got
Scroll up? Sure.
See, the equal sign's not actually.
Oh, there was a y squared I missed in there?
There was a y squared, yes.
There was a y I missed in there too.
And a y. Oh. Okay. All right. Now we're into a tiny bit of trig, sine of xy squared. So partial x, you'd have y squared cosine xy squared. Partial y, 2xy cosine xy squared. Any questions? Doing well? The Mickey Mouses are getting bigger.
This is going on.
Yep. All right, I'm going to keep going. All right, next one we have a lovely natural log. Derivative of a natural log, remember, is just d guts over guts. U prime over u. So f sub x is 3 over 3x minus y squared. F sub y is negative 2y over 3x minus y squared. I see a beautiful whiteboard right here. Well done. Lots of happy faces. Okay. All right. Last one for number 1. Product rule, e to the xy squared times x squared. Well, product rule for the x's. So, f sub x, x squared, y squared, e to the xy squared plus 2x e to the xy squared. F sub y, 2x cubed y e to the xy squared. Well done. Very nice. All right. So are we all feeling pretty confident with our first partials? Yep. Okay. All right, let's talk about the word problem. A cylinder. Did you get all your partials wrong?
I don't know. I think
No, you got it right. The answer key, man, it's right there.
Do you have a question?
Y wrong, but I think I got my x right.
Oh, you dropped this one? You dropped this part was covered up.
I dropped my y. Yeah.
It was covered up by the network down error message.
Oh, okay, that's probably why I didn't see that.
Yeah.
You dropped the one.
Okay. A cylinder is, don't doubt your abilities. It was a network error message cover-up thing. Yeah. Okay. All right. All right. A cylinder is made with a radius of 12 inches and a height of 20 inches. That's a big cylinder. I don't know. Every time I hear cylinder, I think of like cans of fruit. So I don't know why that's where my brain goes. I don't know. Do you guys think of cans when you think cylinders? That's where my brain. So whenever I see like a really big cylinder, I think, wow, that's a lot of fruit. Okay. And a height of 20 inches with a possible error in both cases of 0.2 inches, plus or minus. Just so you know, the plus and the minus end up being the exact same. So you could just stick pluses and minuses in front of your answers and be fine. Find the percent error of the volume. All right, so volume of a cylinder is pi r squared h. We write our differential. Oh, first I don't know why I always just find the projected volume first, but anyway, so there's the projected volume. That's what we want, 2880 pi. So our differential So we have 2 pi r h delta r plus pi r squared delta h. Plug in a bunch of numbers. You get 124.8 pi for your total differential for your volume.
Sorry.
And your error should be around 4.33%. I see it there, I see it there, I see it there, I see it there, there. Beautifully done. On this board, I can't see the 4.33, but I see 50 Mickey Mouses. Uh-oh. All right. All right. That's Sonic. It is pretty good. See, this should make you feel better. Have a little time to draw.
Ooh.
Just a little confidence boost. All right. Great. Have a seat. Well done. Good. All right. Today we're doing section 14.6a, directional derivatives. Well, we're going to learn what a gradient is, but we're not going to learn what a gradient is. Right?
I don't get it.
Okay. So today, all I'm going to do is give you the formula for a gradient.
Yes.
And then we're going to do directional derivatives for the rest of the day. Tomorrow is when we do applications of gradients and we really learn how they get used.
Is that like the PC
Yes. Yes. Okay. All right. Okay, so today I can find and use directional derivatives of a function of two variables. I can find the gradient of a function of two variables. We are also going to watch another captivating video today on directional derivatives and the gradient. You're going to love it. All right. Okay. The gradient is nothing more than the vector of first partials. The gradient is the first partials written in vector form. Partial x, partial y as a vector. Is that, what's the matter, TJ?
I misspelled. Oh, and I wrote it in, so now it looks bad. I have to rip this page out, but I have notes on this page.
Then don't rip the page out and you can deal with the spelling error.
But it looks ugly.
It's notes. We're not. No, don't you dare rip all those notes out.
I'll just like take it to this side and then I'll fix it.
This is over a spelling error?
Yes.
Okay. All right. Okay, so the gradient is written with this upside down triangle symbol. I don't know the name of this symbol. Upside down delta. What's delta backwards? D-E-L-T-A. Atlet.
Yeah, wrong.
All right. So anyway, so the upside down delta symbol, whenever you see that now, that really means the gradient of whatever's next to it. Some. Oh, the name of the symbol? How did you find that so fast? But how did you type it in? Like, oh, it's called Nabla? Nabla. There you go. Okay, so called the Nabla symbol. So Nabla of f of xy. All right, except we don't say Nabla, we say gradient, right? And some sources actually write grad of f of xy. So grad of f of xy. It's another way to write it, but you'll see the upside down triangle almost everywhere. Okay. Vector symbols? I don't know. I used to, I think those, are those the ones I call corner brackets? Yeah. I don't know. Okay, so anyway, all a gradient is a vector of partials. Now that seems really simplistic. How does that change anything at all and make this amazing thing that we're going to talk about for 2 days? Well, I'm not going to get too deep into it. We're going to get into applications tomorrow. You'll see a little bit of it in our amazing video today. So just know that when you take your partial x, right, and if you write partial x as a vector and you write partial y as a vector, whatever that happens to be, then the gradient, right, this is your horizontal component, this is your vertical component, so the gradient gives you this new vector in this new direction, right? And so that's what we're going to learn a little bit more about over the next couple days. So the gradient is a vector whose components are the slopes of the surface in the x and y directions. The slopes in the x direction, the slope in the x direction, the slope in the y direction. It's this new vector.
Wait, so Miss Price,
Yes.
what would it be if we had like the double partial derivative of like x and y?
I don't know what that would be called.
So like
The gradient of the gradient, I don't know. You know, suggest you're writing on the back of a page again, which means if you make even one spelling mistake.
No, I skipped the page.
Oh, did you? You're writing on the back of a blank page?
No, it's just in case, you never know. So I don't like rip another page out. You never know when you
All right. Oh, wait, don't look. Close your eyes. Close your eyes. Somehow I lost the little screen thing. There we go. There. All right. So take a minute just to practice finding gradients. Find the gradients of f of x, y if it equals y ln x plus xy squared at the point 1, 2. So you're actually, first you're going to find your kind of generic gradient vector for any x, y, and then you're plugging your point. Okay. So our general gradient, which would give you the gradient at any point on the function, is I got y over x plus y squared for my x component, and then ln x plus, or for my horizontal component, I should say, and then ln x plus 2xy for my vertical component. Is that what you guys got? Questions? All right, and then you just plug in your points, and so I ended up with the vector 6, 4. any questions on very basic finding a gradient? All right, that's all we're going to do with gradients, except, well, the reason that I'm teaching this little basic part of gradients is we're going to use it a little bit for our next topic. Okay. So, the first partial derivative, ignore the turkeys here. Okay. So, the first partial derivative with respect to x gives us the slope of a surface in the x direction. The first partial derivative with respect to y gives us the slope of the surface in the y direction. But what if we wanted the slope of the surface in some other direction, right? Instead of just x and y. What if we want the slope of the surface that way? So how do we do this? Also, what if we want to find the steepest slope or the shallowest slope or whatever, right? So I shouldn't be going down, I should still be going up, but shallow. So anyway, either way. All right, so today, this is actually gradient. This is what we're going to do today, which is directional derivative. So today we're going to learn how to find a directional derivative, which gives us a slope in any direction. It seems weird that all you have to do is kind of add in this little cosine theta, sine theta vector, and you get the correct slope in that direction. But it works. It actually incorporates, and it's really because the function is defined by x and y. So all of the slopes are functions of x and y. And we're going to see more about how it works on the amazing video that we're going to see in a few minutes. So anyway. All right. So let f be a function, let u be a unit vector, cosine theta, sine theta, where theta is measured from the positive x-axis. Then the directional derivative, which is written as d sub u of f of xy. This is standard notation. All books use the same notation. D sub u of f of xy equals partial x cosine theta plus partial y sine theta. So your directional derivative is your partial x times cosine of theta plus your partial y times the sine of theta. So I have a quick question here and then other things to point out. But so for example, suppose theta is 0, right? Remember, theta is measured from the positive x-axis. If theta is 0, what is your directional derivative? It's just partial x, right? If theta is pi halves, what is your directional derivative? It's just partial y, right? And then when you switch thetas to other values, you get those other values in between. All right. Okay. All right, does everyone have this? This is the key part to write down. All right. Any direction, the direction of theta. Yep, gives you the slope in the direction of theta. So, but it doesn't have, well, that's what we're going to get to next. So, anyway. How does the directional derivative relate to the gradient? So this is why I taught you gradient. Different books do this different. Some do gradient first and then directional derivative. Our old book did directional derivative first and then gradient, which was silly because the directional derivative is actually most easily calculated and defined with the gradient in it. So that's why I taught you gradient first, so that we could use it to find directional derivatives. So if you think about it, if the directional derivative is partial x cosine theta plus partial y sine theta, and remember that your u, this is the vector that gives you the direction that you're going in. If your u is cosine theta sine theta, then what is the directional derivative really? It's just the gradient dot u. It's just the dot product of the gradient and your direction vector u. So this actually kind of comes in handy for calculating directional derivatives, is knowing this version of the formula. that it's just the dot product of the gradient and your direction. You think of u as your unit direction vector. Now, here's the part that I think is kind of nifty. U is originally presented as this vector cosine theta sine theta, where theta is the angle, of the direction you're looking at. But U doesn't have to be written as cosine theta sine theta. Cosine theta sine theta is automatically a unit vector, right? We know that because cosine squared plus sine squared is 1. So we know that's a unit vector, but it doesn't have to be written in trig form. U can be, if I know that I'm going in the direction of like -5, -2, right? This way, as long as I get a unit vector that's in that direction, that can be my U. It doesn't have to be in terms of an angle. It can be in terms of, components, right? It can be either way. So, that being said, as long as it's got to be a unit vector though, otherwise it doesn't work because it changes your slope then. All right, use the dot product version. So I want you to use this version to find the directional derivative of f of xy equals 3x squared minus 2y squared at the point -340 in the direction of a vector that starts at -340 and passes through the point 0, 1. Whoa. So, you're going to need to find two things. You have to find your gradient, which I know you can all do, piece of cake. Then you're going to have to find your U, which is a unit vector in the direction you want. All right? So you want a vector that goes from here to here. U would be a unit vector in that direction. Here, I'll raise this up so you can see better. I'm going to pause this. Okay.
And minus 16 y.
So I worked on my unit vector first. So my vector was the one that starts at -340 and goes to 0, 1. So I did q minus p and found vector pq. It's been a while since we've just subtracted to find a vector, right? So I found vector PQ. Remember, the magnitude of PQ, this squared plus this squared, square root. So 9/16, 25/16, so 5/4 is the magnitude of PQ. So you do this divided by 5/4, and when you clean it up, you get 3/5, 4/5. Okay. Any questions on finding a unit vector in the right direction? All right, so that's my U. All right, so then my partial x was 6x, my partial y was -4y. Do the dot product, and you end up with 18/5 x minus 16/5 y. Yes, Sophie?
Does it work if you get -3x,
The problem is that's not in the right direction.
Yeah, but like how would you know?
It's always end minus beginning to
Yeah.
get into the right direction. There's no like negatives are okay if it's the right direction, but the problem is if it's, there's no way to look at it and say that's the wrong direction. You would just have to know by your work if it's the right direction. Yeah. So you can have negatives in your unit vector as long as it's pointing the right way. Okay. All right, and then the last thing you have to do is plug in your points. Right, and so you plug in your point, and there's your slope. This would be the slope of your surface in the direction of whatever that, in the direction of 3/5 surface, in that direction. So the slope of your surface means going down in that direction. Okay. All right, one more. Find the directional derivative of f of xy equals 4 minus x squared minus 1/4 y squared at point 1, 2 in the direction of pi thirds. So I've given you the direction vector here. It's already in unit vector form. All you have to do is a dot product. might want to simplify the cosine pi thirds and the sine pi thirds. All right, so if you find your partials, so partial x is negative 2x, partial y is negative 1/2 y. I went ahead and simplified cosine of pi thirds, which is 1/2, sine of pi thirds, which is √3/2. And so this was my kind of generic directional derivative. So it gives you the derivative in any at any point in that direction, but at any point. So then I plug in the 1, 2, and I end up with, I got -1 minus √3/2. Wait a minute.
Where you like swipe your
So when
hand
you plug in
and
the
someone
future, I
no. The person who's moving that way.
Yeah, so like if I do this, you go that way, then
And you,
yeah.
alright, I'll go first. Oh.
Dot products you just had.
Alright.
Good. Any other questions? All right. Okay, one more. Find the directional derivative of f of xy equals x squared sine of 2y at point 1 pi halves in the direction of 3, -4. All right, so, by the way, I revealed, I thought that was going to be later. Okay, so is v, this is our direction vector, but the direction vector has to be a what? Unit vector. If your direction vector isn't a unit vector, you're going to get the wrong slope, right? So you want your direction vector to be a unit vector so that it's not changing the magnitude of your slope. So,
How do you know that's not unit vector though?
well, we have the square root of 9 plus 16 is not 1.
Yeah, okay.
Yes. Okay. All right. So, anyway, yeah. So you end up with a unit vector of 3/5 -4/5. And then you can do your cross product. So 2x sine 2y times 3/5 plus 2x squared cosine 2y. Oh, cosine 2y times 2 times x squared times -4/5. And then plugging in your points, you end up with an answer of positive. I got positive 8/5. Yeah, it's a negative 8/5. Was it positive? Okay.
Positive.
All right. Okay, good. All right, good. All right, now, this woman on this video, I like this video because she impresses me because she's so good at drawing in 3 dimensions. So, all right, I'm going to get it started and then I will turn the lights down. Okay, so hang on. Okay. All right, so
It has 2 dimensions.
okay.
Now, I can immediately define our first major player in this saga. I can tell you what the gradient is. So this is the symbol for the gradient at the point x naught, y naught. That's a Hebrew symbol. It's a vector. And the components of that vector, it's a 2-dimensional vector. The components are the partial derivatives at the point. Partial f with respect to x, and the partial of f with respect to y. Well, that's a 2-dimensional vector, not a 3-dimensional vector. So if I wanted to draw it, where should it be? Well, it doesn't stick up like that. It has no z component. So it is in the plane they're in a plane that's parallel to the xy plane. So it might look like this. I could draw it up here if I wanted to. I don't know yet what direction it points in, but nevertheless, the important thing is that it's a two-dimensional and not a three-dimensional vector. So now that we've mentioned the partial derivatives, let's come back into 3 dimensions and remember what those partial derivatives mean, at least geometrically. We're not going to calculate partial derivatives. We don't need to do that right now. So let's start by drawing a line through the point x0, y0, parallel to the x-axis. And if you think about it for a moment, this line is actually y equals y0, because we're freezing y but letting x vary. Now we can also extend this upwards and get a plane that's parallel to the xz plane, but I don't want to clutter up my picture too much. But when we do that, I like to think of this as kind of coming up and slicing through the curve, or through the surface. And what we get is a curve. So now we have a picture very much like the picture that we had in 2 variables. We have an axis and we have a curve above it. Now, because I'm assuming that this surface is smooth, and I am assuming that, there's going to be a tangent line to that curve at that point. And what is the slope of that tangent line? Well, it's the partial derivative with respect to x at the point x0, y0. Okay? Now, what about the partial derivative with respect to y? Well, we do the same thing, but we draw a line now parallel to the y-axis, and if you think about that for a moment, this is x equals x0. So this is the line x equals x0. We can bring it up into a plane, and it too is going to make a curve, and that curve has a tangent line, and the slope of that tangent line is the partial derivative of f with respect to y at the point x0, y0. Now, a perfectly reasonable question or thought at this point is, why do we only have to draw lines parallel to the 2 axes? Why can't I draw any line through that point and do the same thing? Make a plane, cut through the surface. What would I get? I would get another curve. And I want to be able to talk about the slope of the tangent line to that curve. So in order to do that, and we're getting close to our second player here, the directional derivative is lurking in the shadows at this point. So what I want to do is think about this blue line and think about the blue curve, and I want to figure out how to find the derivative of this curve at this point. So how can we do that? Well, first of all, let's call this line L. It's not quite like the x or y axis. We don't really know which direction is going to be positive. But let's take a vector, u, and let's assume that u is a unit vector, which means that it has length 1. That just makes certain things easier. And let's let u have components a, b. Now, how do we write the equation of that line? Well, it's a line in the xy plane, so we should be able to write it in point-slope form or in slope-intercept form. But the easiest way for our purposes is to write this line out using parametric equations. And let me show you what those look like. So t is a parameter now. Where does t range? Well, it can be any real number, but let me try and convince you that that describes this line. Well, when t is 0, we get the point x0, y0. Fair enough. But what happens as t varies? Well, when t is positive, we're going to go in one direction. Negative, we're going to go in the other. You still might not be buying this, but let me remind you that this is what we're calling x. This is y. And when you have parametric equations like this, we could solve for t, right? We could solve for t. In fact, t is x minus x naught over a. And then we could take that value of t, plug it in here, and just glance at what we get. We get y is equal to y naught plus b times this. Well, there's an x in there. And if you rearrange things a little bit, you will see, indeed, that we get an equation of the form y equals mx plus, well, I can't use a b because I've already done that, but plus c. So this indeed is a line through the point x naught, y naught in the direction of u. Well, now we want to figure out how to find this derivative. Well, let's think about that. Each value of t gives us a point here. And here's our function f, computed only at the points along that line. So let's see what that looks like. Okay? We have the variable t. Once we pick t, we get 2 points, x naught plus at, y naught plus bt. Well, we get 2 coordinates. This is x, and this is y. And then we plug those in, and we get f of x naught plus at, y naught plus bt. Well, what do I want to find? I want to find df.
Oh, we can watch the last minute. It's core time.
With respect to t, when t equals 0. And that, my friends, is going to be the directional derivative in the direction of u of the function f at the point x naught, y naught.
We missed the final thing
Well,
where
that
she
might seem
derived
like a very
it.
hard thing to
Okay.
calculate. Let's take away our picture, which I hope has been helpful. And remember,
All right.
another very useful concept coming to us via
Hey, look what she's
single
using.
variable calculus and then multivariable calculus. How do we find a derivative going from the top level to the bottom level? At least that's the way I like to think about the chain.
I think I've lost
Well,
everyone.
we have to
All
pass
right, I'm
through
turning
the
it off.
Okay?
I'm shocked you guys didn't find this fascinating. All right. Well, anyway. Okay. Well, she's showing you how the directional derivative is derived, which I think is kind of neat. So it uses chain rule in order to derive the directional derivative. But that's all right. There we go. She's plugging that stuff in. And I'm dying to continue on, but that's okay. Notice, remember, AB is a unit vector in the direction that you want. Okay, amazing, amazing. All right, good enough. Okay.
I can learn everything.